In this video, we will use factorial, double factorial, and the gamma function to generate the trendline polynomial of this function x times e to the power x. We begin with the dataset, which is array formula of the x values times exponent of the x values, and enter. And we'll chart this. Insert chart, and we'll use scatter chart. And show the trend line. So use row 1 as header and the trend line. Polynomial to the 6th degree. No, 6th degree. And show the equation as label, the legend, position at the bottom. And here's our trend line and trend line polynomial. Next, we generate the Taylor-Maclaurin series sum of this, which is the summation of a times x to the power n, where n starts from 0 to infinity. We can go as far as 16, which is good enough. Now we continue with the coefficients, starting with the factorial, which is equal to array formula of the n divided by factorial of n, and enter. Next, the double factorial. So array formula of the n divided by, there are two parts now, and they are both double factorial. So fact double of n times, again it's fact double factorial, but this time there's a negative 1. So minus 1 factored in. And finally, the gamma function, which is array formula 1 over gamma of the n values, and enter. So we'll correct this error. This should be 0. So for this case, we'll have a function called if function. If value of n is G3 to G19 equals 0, then 0, otherwise calculate. Now it's corrected. And we'll copy the same condition right here. So this, from this portion up to this, copy it as well. Copy and paste here. Then enter. Now they're all corrected. Now we continue with the expansion, which is array formula series sum of the x values raised to the power n, where n starts from 0, incremented by 1. And the coefficient, there are 3 to choose from. We'll start with the factorial. And we show the trend line. We'll modify this. Edit chart. Customize. Series. Trend line. Polynomial to the 6th degree. And use the equation as label. And here you have the trend line all in the same loop, all collinear. We'll calculate this regression coefficient using the LINEST function, beginning with the power. So that is transpose 0 to 6. And the elements of the matrix, which is equal to array formula of the x values raised to the power 0 to 6. And enter. And we calculate LINEST, or the polynomial regression coefficient. LINEST data y and data x. And enter. That's correct. There must be some error here. This is data y and this is data x. Oh, this is our data x should cover this. And the expansion, LINEST data y and data x. And enter. We'll compare. Coefficient of x to the 0, 0, because this is very small. Times 10 to the minus 33 times 10 to the minus 32. This is very small. So that's already 0. Coefficient of x, 0.998. Coefficient of x squared, 1.01. Coefficient of x cubed, 0.456. Coefficient of x to the fourth, 0.02, coefficient of x to the fifth, 5.16 times 10 to the minus 3. Coefficient of x to the sixth, 0.0243. Suppose I will use the double factorial as the coefficient. So we'll change this. This time I'll use the coefficient, the double factorial as coefficients. The values, the polynomial regression coefficients are the same, the data sets are the same, and the polynomials are the same, and the trend line remains unchanged. They are still collinear. Suppose I will use the gamma function. So I will replace this with the gamma coefficient. So this is the gamma. That was the double factorial. This time is the gamma. Again, the polynomial regression coefficients are the same. The polynomials are the same. The trend lines are collinear. And the data sets are all the same. This completes the use of double factorial, factorial, and gamma function in generating the function, the Taylor-Maclaurin series sum and LINEST polynomial regression of x times e to the power x.